evening, everyone. So today we're going to do section 7.4, this is integration of rational functions by partial fractions. Rational function is just something that says x plus 3 over x squared minus 2x minus 8. It's just an example of a rational expression. And so we're going to learn how, if there's integral symbols in front of these, how to find the antiderivative. You're going to notice with these problems, 90% of it's just going to be algebraic manipulation. So in section 7.4, really, like 90% of the problem will be algebraic manipulation before you even get that integral thing to begin and get your, find that first step of the antiderivative. That's what we do. We end up getting things like this, and we break it up into partial fractions with a summation. So first thing we got to learn is how to recognize how to break up each scenario. So we look to see in the denominator, we won't worry about the numerator, it'll be the denominator. There's just some way you can factor this. So we'll be doing some factoring in section 7.4. So this example, I didn't put an integral symbol down yet, but the idea of how I could break this up. Can I break this, or excuse me, factor that denominator into two linear factors? What would it be? X minus 4 and x plus 2? Understand with that? Great. These are called linear factors. If you want to put that down, just the language in 7.4, you can recognize the different types of factors. Okay? That's a linear factor, that's a linear factor. And you go, why? Well, it's x to the first power. That's x to the first power right there. There's no x squared. When you set this up, we're going to put a constant a over one of the linear factors and a constant b over the other linear factor. It'll be that simple. And then we'll work the problem. All right, so we won't solve this. In a few minutes, we will solve an actual integral problem. But just, we got to learn how to set these things up. How are we going to break these expressions up into partial fractions? This is one example where you had the two linear factors. And I'll just put constant a over this plus constant b over x plus 2. And eventually, we'll figure out the actual numbers for constant a and b through algebraic manipulation. So that's just one setup. You okay with that? All right. What if you have something like, let's say, okay, you got a 3 on top, x squared, x minus 1. Well, it's already factored for us. Nice, huh? This right here is called a linear factor. You agree? This x squared, isn't that really like x minus 0 squared? True. So, all right, linear factor. Let's refer to this x squared as a linear repeated factor. That's what we'll call it, a linear repeated factor. And the way we're going to have to set this up is that x squared is just x times x, right? I'll put an a over a solo x plus a b over a x squared plus a c over an x minus 1. And you bet, because that x is really x times x, isn't it? X dot x. Crazy thing, students sometimes wonder, wait, why did you put a over x plus b over the other one? Because we think of this as a linear repeated factor, right? A linear repeated factor. So if you ever see linear repeated factors, you have to put an a over the first power and then a b over x to the second power. And I'll just give you another example. What if it was like 5 plus x over x to the third times x minus 4 squared. This is linear repeat factor. And this is also a linear repeat factor. And how would we set this one up? A over just the x. Then I have to do plus a b over a x squared plus c over x cubed. I got two more, don't I? because this is also a linear repeated factor. So I can do plus d over just the x minus 4, and finally plus e over the x minus 4 squared. This would be the setup when you're dealing with what we call linear repeated factors. Okay? Don't worry, we're not going to work a problem like this today in terms of it. It'll take forever. But as long as you see the craziest scenarios, you're going to be comfortable with the problem you're doing. So you know how to deal with linear factors, and you know how to set up things when you have these linear repeated factors. This was a linear repeated factor, that was a linear repeated factor, so is this one, right? We think of that x cubed as like x minus 1 cubed. We have to do one for each x squared, x cubed. Can you imagine it was like x to the 7th? Yeah, you're like, oh my gosh. You have an a, and a b, and a c, and a d, etc. Go ahead.
Do the same thing with the linear repeated parts on the top?
Nope, we'll never worry about the top. Great question. It's all going to be about just taking care of that denominator, because you go, how do we add fractions in math? It's all about common what? Common denominators. And that's why it is all about that denominator. Yeah, this is going to be involved eventually. But our eyes, with these partial fraction problems, when we start out, we look right at the denominator. Okay? These rational expressions. Now there's one more type. We've talked about linear factors and linear repeated factors, right? And you're able to recognize them. What about a non-linear factor? So here's an example. X times x squared plus 2. And I'll just put something on the top. 5 plus x. All right. And we're going to break this up into partial fractions with constants a's or b's and c's, etc. But something new has now emerged. Do you agree that's a linear factor? That'll be easy. We'll just put an a there, right? This. In the real number system, we can't factor that into linear factors, can we? Excellent. You all observe that? In the real number, I mean in the complex number system, you can with i's. Everybody's familiar with the complex number system with the imaginary numbers. But in the real number system, we cannot break that up into linear factors. So we're going to have to deal with something. How do you deal with the, just call it a non-linear factor, if you ever see one? All right. Well, let's first take care of the linear factor. A over x. Is everyone okay with that? And again, we're ignoring that numerator, right? This is how you set it up for a non-linear factor. I'll put down that x squared plus 2, but look what I wrote. bx plus c. And that's how to set up the problem when they have a non-linear factor. In the numerator, we're going to write bx plus a constant c. And eventually, today, everyone, we're going to be finding the constants a's and the constants b's and the constants c's. And once we do that, we'll have integrals we can solve, actually rather easily. So 90% of these problems just going to be manipulation. Hey, one more with non-linear factors. What if you had x plus 3? So I'm going to go all out here, okay? I think I'll give you a linear repeated factor there, right? That's a linear repeated factor. How about x squared plus 3 and x squared plus 5? No, we won't solve a problem like this today. Can you help me set this up? Help me out with the linear repeated factor. A over x plus b over x squared. Excellent. Now, how would you handle that x squared plus 3? You are good. Cx plus d. It'll be x squared plus 3, and it looks like we're going to need one more of these. Ex plus all over x squared plus 5. You got it. Now we'll work a problem. If we don't see anything this crazy, could work it would take care of. Eventually we'll find these constants a's and b's and c's and d's. We have to break these things up. So, all right, integration of rational functions by partial fractions. Let's get to it. Let's look at a problem. You'll see one of these scenarios. The key is we will just focus on that rational expression. Break it up. Once we break it up, we're going to put it back with the integral symbol. All right? So that integral symbol is just going to sit there for 90% of the problem. So once we have this thing set up, got the a and b's and stuff, we'll come back and put the integral symbol and set it up. Okay? Okay, here's the first one. We have x plus 5. Or x squared minus x minus dx. Now think about everything we've done in this course too, as you're looking at this problem. It's like, well, how would I recognize this as partial fractions? You see the rational expression? We've seen rational expressions before many times. So your first intuit, your first thought might be to do a u sub or something, but you notice a u sub wouldn't work. Like, what am I going to u equal to x squared minus x minus 2? Right? It's not going to work out with this problem. So let's go at it. We'll come back to that integral symbol. This is the problem at hand. But we're just going to start out looking at this x plus 5 over x squared minus x minus 2. First thing is, can you factor the denominator? Because it wasn't factored. What did it be? X plus 1, x minus 2? So that's a key step. Is that okay how we factored that? Does it matter the order of these? Nope. So don't worry if you're studying with a friend and they put this here and that there, so you're like, our A's and B's are different. You're still going to get the same right answer in the end, right, as long as you factor it. So you're going to break this up into partial fractions. And once you have this broken up into partial fractions, we'll come back, replace it with that expression to perform the integral. How do you break this up? What letter do you use here? Hey, A over x plus 1 plus b over x minus 2. You got it. I mean, that's a key step. You knew exactly how to set this up. Those were two linear factors, no repeated linear factors, no nonlinear factors. But now we've got to algebraically figure out what? The A and the B. So what I'm going to do, everyone, is I'm going to have to look at, well, to add fractions together, wouldn't you need a common denominator? So I'll write this again. X plus 5 over x plus 1, x minus 2. I'll write that again. And I'm going to get out the yellow chalk. A common denominator. What would I have to multiply in the top and bottom there? So I'll put that on with the yellow chalk. So now we're working towards getting the constants A and B. Well, we're thinking to ourselves, well, how would I add these two fractions together? Well, I'd have to multiply x minus 2 over x minus 2 there. And here I'd have to multiply
Plus 1 over x plus 1.
Thank you. X plus 1 over x plus 1. Okay. Well, I want to color code that. Put that in yellow. We now have the common denominators, don't we? Step what? So that's the step 2, I guess you would say. First you set it up properly with the A plus the B. Now we're thinking about, oh, I need common denominators. How would I be able to add these fractions together to get common denominators? So far, so good? Now, everyone, here's the cool part with this process. Even if you don't like denominators, are all the denominators equivalent? I want you to just examine this for a second. Look at it carefully. That denominator, they're all what? Equivalent. So all we're trying to do is figure out what the heck is letter A, and what the heck is letter B. So our concentration is now just this numerator. Would you put a box around this entire numerator? That's our problem in here. This is where our eyes are now. Just put this in eyes. Just that. And I'm going to rewrite that. What about those denominators? I'm just trying to figure out A and B. If these are already equivalent, and we're working this problem, we're saying, let's just examine x plus 5 must equal to A times the x minus 2 plus the B times the x plus 1. You agree? x plus 5 must be equal to a times x minus 2 plus b times x plus 1, right? Because all the denominators are the same. So now we get those denominators out of the way, and this becomes our focus. And we're going, where are we going with this? We haven't even come close to doing that integral symbol. We're just trying to find a and trying to find the value b. So that these two sides of the equal sign are equivalent. All right? Now, the one method that works every time is the method of solving the equation by equated coefficients. The method of equated coefficients. And you go, what's that? What's in front of that x?
1.
It's invisible 1, okay. And that's a constant 5, right? So what I'm going to do here is I'm going to distribute this. ax minus what? 2n plus bx plus b. And you're like, where is he going with this? I'm trying to equate coefficients on either side of this equation. So leave that x plus 5 there, but can you do me a favor on this right side now? Now that you distributed these, can you collect everything that has an x with it? And then leave the constants at the end. So in my next step, I'm going to write this as ax plus the bx. Don't see that? And what's at the end there? A minus 2a plus the... And what's this equal to over here? We're almost there. So from here downward, I'm now trying to look at equating the coefficients. What's in front of that x again? Or 1. So boy, it would be nice if we can write this right side here as just a solo x. Can I factor something out? I can factor out an x out of that. What would you be left with? I'm going to write a plus b x. And just leave this constant negative 2a. All right. Now, we're ready. What's in front of the x on the right side of the equation? A plus b. What's in front of the x on the left side of the equation? A 1. I'm going to put it. So now we're just going to write a plus b must be equal to 1. A plus b must be equal to 1. Hey, I'll put a wall here. What else has to be true? And what's the 5 going to equal? The 5 is the constant. That's going to equal everything that you have up here on the right side that doesn't have an x with it, which is the negative 2a plus b. And are we getting really close to figuring out a and b? All right. But I mean, this method I'm showing you right now, we're going to get a and b. But the method we're using, this idea of equating coefficients. You follow me what I'm saying? Coefficients, like the coefficient to x on the left side and the coefficient to the x on the right side. And I'm setting them up so I can solve for these a's and b's. All we have now is a system of equations that we can solve. We'll get a and b. The reason I showed you this technique, because this works on all the problems. This works on all the problems. I want to show you that first. Now, we got to solve that system, don't we? How do you solve a system a plus b equals 1? And 5 equals negative 2a plus b. Some of you might do substitution method. Does anybody like to do the add out method? We taught that in algebra, like the add out method, where you can write like, I'll put a plus b equals 1, and then I'll put negative 2a plus b underneath it equals 5, and you can just add down and hopefully something will cancel out. If I add down, does anything cancel? Now, who's seen this before? They call it the elimination method. You don't have to do it. Can you solve this by substitution? Absolutely. I could say a equals what? 1 minus b, and substitute the 1 minus b for the what? For the a. That's totally fine. But if you've never seen the elimination method before, I can set these up like this. Unfortunately, when I add down, none of the letters cancel out. Anybody got any ideas?
Multiply by a constant.
Yeah. Want to multiply the top by, what'd you say? What'd you suggest?
By 2.
He says if you multiply the top by a 2 here, 2a plus negative 2a becomes what? 0. It goes away. But you do have to multiply the 2 everywhere across the top. That's what he's saying. You also could have multiplied a negative 1 because it would have made the b what? A negative b, and then a negative b plus b is what? 0. But I'm going to use Nicholas's idea. I like it. So I'm going to multiply negative 2 on the top. I'll just put an arrow. I'm going to multiply a negative 2 to that top part.
Hi.
And what would you get? Oh, a positive 2, oh, thank you. We're gonna multiply a positive 2 to the top so that they cancel. We're trying to eliminate the a's. I get 2a plus 2b equals, you gotta multiply it to the 1 too. 2, and what's underneath it? Negative 2a plus b equals 5. Okay, add down. What's 2a plus negative a? C. What's 2b plus b? 3b. And what's 2 plus 5? 7. So what's b equal to?
7/3.
7/3. How do you get that?
So we add
Yeah, because there's stuff all over the board. He says plug it back in. Great call. Where would you plug this? 7/3. Right there? So if a plus b equals 1, and a plus 7/3 equals 1, what would a?
-4/3.
-4/3?
Yep.
When b equals 7/3, we're saying, well, a plus b must add up to 1, and the a value must be? Yeah, and it becomes a -4/3. You all agree? Can you get a and b? And let me just look at the right side of the board. We have yet to do the what? The integral, right? We have yet to perform that integral. We got everything set up properly. So now I'll go back in. Listen. And you relieve. It's now time. What am I going to replace this with? That. But guess what I get to put for A? -4/3. And for B?
7/3.
7/3. So I come all the way back where this thing was just sitting forever waiting. I'm like, hey, I'm going to break you up into partial fractions. Let me just make sure I put the a over the proper one, right? I put a over this, so it's going to be -4/3 over up. Plus, what's the b? 7/3? Does anybody know how to do these intervals? How do you do the integral of 1 over x? You'll find them easy. What's the integral of 1 over x? Natural log of x plus 1. These don't even involve u subs. If they can do just u subs.
Pull out the top as a constant.
That's right. So I can think of this as -4/3 times the natural log of x plus 1. And what will be this antiderivative? 7/3 times the natural log of x minus 2. I mean, that easy. You'll know, then we'll have our answer. And I'll write that. So you go, this was the majority of the problem, wasn't it? By the way, if you're wondering why we didn't need a u sub, you'd only need a u sub if the number in front of that x was something other than the 1, like a 2 or a 3. Then you got to do a u sub to deal with that, because in this case, that's the the actual antiderivative. So let me write this. You're saying just leave that -4/3 in front, right? -4/3 natural log of x plus 1. Oh, we got to put bars, don't we? Plus 7/3 times the natural log of x minus 2. Let's see. Hey, these absolute value bars, if you're curious why we always write them, because let's say you had, what, a negative value in there in that expression? Well, -1 minus 2 would be -3, but what's the absolute value of -3? 3. And you can still work out the problem. So if you want to see a definite integral, eventually we will put a problem down today with a definite integral. Awesome. Hey, super job with this problem. This problem, if you're curious, this is like number 9, this is like number 10, this is like number 11, this is even like number 12 from the textbook. All right. Can I raise?
If on the test, if we know how to, are we able to use like a matrix to solve that?
Sure.
Then we know how to use is that?
Absolutely, you're talking about right here, right?
Yeah.
So when he has knowledge of solving system with matrices, with a calculator, you can definitely do that. You know? To me, it's like you're being what? You're using your math mind to apply mathematics. I like that. Hey, there's something else I gotta show you. Remember we got down to here? Where I took this with my eyes, and I just didn't ignore the denominator, kept writing it out. I want to go back to this. Want to see this part right here? There's a quicker way to solve that. And I want to show it to you. Now I know you're going, why didn't you show us that the first time? Because it doesn't work on every one. Problem. But by golly, if you want to work it that way when you can, please do it. It's a lot quicker. See all the work I did? It took a little math here, algebraic manipulation, to get this 7/3 and this -4/3. There's something I need to show you. Please feel free to do this when you want. I'm going to wipe out from here down. Once we had this set up and just looked at the numerator, okay? You ready? All right. You watch. We're going to get the same number. Okay. This is a cool trick. You want to call it a trick? What we do is we mathematically think, well, we got an equation here. How about let's just brainstorm a value of x that makes one of these two things equal 0. I want you to brainstorm a value of x, I don't care which one, it makes either one of these turn into a 0.
2.
2. I'm going to start with that. So I'm going to agree if you let x equal 2 here, then this part right here becomes into what? 0. So I'm going to put if, because it's like, hey, if x equals 2, what happens to this math equation? Now make sure you do the entire left side and the entire right side. And you'll find this way quicker. Well then what would this be? 2 plus 5, oh that's 7. This turns into what? 0, because 8 times 0 is 0. Plus, now you gotta put it right there. What's 2 plus 1? And you're like, are you kidding me? Look what you already got. 7 equals what? 7 equals B3. Are you kidding me? What's B? Divide it 3 on this, that's what's B. See how quick that was? Way quicker than the other. Now, we do need the other number, so I'm going to leave this. Well, brainstorm an idea. What could make this 0? Was everyone okay with what we did? You go, you're allowed to do that? Absolutely. You're just trying to figure out a way to figure out what would be in this process. So we like, oh, what would make one of these zeros? Because zeros are easy to deal with. What else? Way quicker. Hey, go over here. What would make this 0? What x value? So let's do that. What if x equals -1? Maybe this time I don't have to do as much writing. Plug in -1 right there. -1 plus 5 would equal 4. A times, what's -1 minus 2? -3 plus, what happens when you put a -1 there? 0. And what do you get for a? I mean, come on, look at the writing. Let me step away, get out of the way. Compared to what I had before. Wasn't that a lot quicker? Exactly. That's the idea. You go, all you're trying to do is get the A and the B. And use, like, usually you're thinking, I'll use matrices. My gosh, you can also do this as well. But the reason I showed you the other way first, because that way, if this worked every time, I'd be doing this every time too. Connor.
How do you know when this doesn't?
Oh, it's going to be on a more, it's a good question. It's hard to look at a problem and recognize it is. It'd be a little bit more complicated. This just had, what, 2 linear factors? This works every time if you have 2 linear factors. How about that? But if you start getting like, how about this? If you get a non-linear factor, remember those with the x squared plus 2? You're going to find that just doing all this wouldn't hold. But, hey, I still want you to think about this. Because you might do this just to get one number. So please, everyone, be always thinking about this. Because you might just do this to get one of the letters. Because what if there's an A and a B and a C and a D and an E? And you apply this process like, I'm just going to let x equal 2. Boy, if you can just get one letter in mathematics, and that's solid, it's like, okay, I got one letter out of the way, I only got a few left now. And I'll make sure to show you a problem like that today. Where you go, all right, we're going to have to use the process of finding those, it's called equating the coefficients. Everyone okay with this too? Cool, and you can leave the answers like this. We will do a problem where it has limits of integration. I'm going to pick that problem right now. So 7/4. Let's look at one, but this, let's put some numbers on it. So that you can actually check this and check your calculator like definite integrals to see you get the same value. The beauty is though your calculator is going to put it in decimal form. We'll have it in exact form, won't we? We'll have the exact value. All right. And when this is number 12. That answer's not in the back of the book, is it? And they got an x minus 4. And that's all over. X squared minus 5x plus 6. Oh, I forgot to write dx. And the limits of integration? Just 0 to 1. You stare at it and you're thinking, oh, is that a U sub? Does not look like a U sub. Is that integration by parts? That does not look like integration by parts. But we do see a rational expression, so we're now thinking partial fractions. Okay. Let me get this all out of the way. First step, can you factor that? This entire thing will be just algebraic manipulation. X minus 4 over, what's that factor?
X minus 2.
Cool, I'm going to use that order. Again, if you wrote, what if I wrote x minus 3, x minus 2? It's okay, you'll still get the right answer. I always say just be careful when you're studying with a friend. If they put them in different, you're going to have a different A and a different B. But in the end, you'll have the same answer. All right. A over 1, B over the other? Add them together? Sounds good to me. All right, we're getting this thing started. All right, that's the first step. That's the 7. But now, it's all manipulation. Can you find the A and B that makes those two sides of the equation equivalent? And we go until we find it. All right. So how do I add common denominators? Let's see. A, x minus 2, what do I got to multiply? X minus 3, x minus 3. Plus b over x minus 3 times f. X minus 2, x minus 2. A lot of writing with these problems, huh? If you do find yourself doing 2 steps at once, that's totally fine. 3 steps at once. And if somebody can just look ahead to see what's coming up, that's fine. And now it's ready. Where's my focus? Just the top. Just this. Pull it out. That's what we're working with. And notice there's an equal sign in the middle. Make sure that equal sign doesn't get erased. There's an equal sign in the middle. There's our focus. In fact, I like to write it again. X minus 4 equals A times x minus 3 plus B times x minus 2. I don't know about you, but I'm all in favor of, because this has 2 linear factors, Connor and everyone. Let's go for that quick method where we do the if x equals. Because it's quicker. So ready to do it? We're just trying to find A and B. So I'm going to play around with it. Here we go. If x equals 3, what would happen to all this math? What would that side become? 3 minus 4 is -1. A times 3 minus 3 becomes a 0. Then you have a b times a 3 minus 2, which is a 1. We know what b is. Man, that was fast. What's b? Thank you, author James Stewart, for giving us a nice introduction. By the way, that's why I wanted to start with a number that wasn't an integer. Sometimes you don't get integers, right? Now, what's the other if? If x equals 2. All right, start over here. 2 minus 4. 2 minus 4 is -2. Equals a. 2 minus 3 is -1. Plus, what's that turn into? By the way, I wasn't taught this way, if you're curious. I'm sure my teacher was like, she wanted to make sure I did everything so it worked every time. I didn't know this little quick thing. It's fast. What's A here? Is A just 2? It's right. Put these here, replace that. It is ready. All right. A over x minus 2. What's that? 2 plus B over x minus 2. Ah, we don't need to use those. Try it out. We'll finish it up. You go, wait, there's numbers. Oh, we'll plug those numbers in. Two natural log of plus -1. You just want to put -1? Okay. -1 times the natural log of x minus 3. And now it's a definite integral. I will plug in the values of 0 and 1. I'll substitute 1. Subtraction sign. Make sure we also substitute the 0, right? Because you notice, you put zeros in here, you still get numbers. Okay. It is now ready. 2 natural log x minus 2, absolute value. Minus 1 times natural log of x minus 3 with the absolute value bars. I get 2 natural log of, what's 1 minus 2? It's -1, but there's bars around it. What's the absolute value of 1? I mean, what's the absolute value of -1? Anybody know the natural log of 1? All right, cool. That's going to turn into 0. I'll leave it like that. This is just for your notes. But just so, at first, maybe I'll just plug all the numbers in. Now you got minus ln of, plug into 1, -2. Subtraction sign. And now you're going to plug in the what? The zeros, right? So I'm going to plug in the zeros. 2 natural log of -2 minus, and I'm forgetting something on purpose, so people catch it. 0 minus 3 is what? -3. Now, when I screwed up, it's a common error on tests. I want to make sure no one makes it. So I'm just plugging in numbers, right? Yeah, this subtraction sign has to distribute all this, right? But why did you just say plus ln 3? Okay, let's finish this up. 2 ln 1, which is 0, minus natural log of 2, minus 2 natural log 2. Still in the bar, so I'll write ln 3. That's 0, right? We got it. But when I bet you back, a book doesn't write it that way, do they? Aren't there log properties you can write a little bit better? But that's pretty daggone good. Like, students always like, yeah, can I leave it like that? I'm like, yeah, but can you erase the 0? And I'm like, all right, yeah, I'll take that. That's exact. That's exact, right? But before we just leave it like this, let's talk about at least writing it in simplified form. ln 3 minus ln 2 minus 2 ln 2. Okay, can I start here? If anybody need to move that 2 there? You can rewrite this as ln 4. ln of 2 squared, which is ln of 4. I didn't know if you knew that log problem. I know sometimes students get nervous, like, do I have to do that? It's okay, no. I'll be honest, I'm okay if you don't do that. Anybody know what you can do with that? It's a property of logs. Did you know you can write this as one log? Natural log, you got to do, is it multiplication or fraction? It's the fraction. So I can rewrite this whole problem as natural log of 3 over 2 minus natural log of 4. Can I go even further? Yes, you can. So right now I'm just manipulating. And this is final answer. Natural log of, what's 3 halves over 4? 3 over what? 3/8? But yes, so when I am me, I'm fine if you just left it blank. Right here. Sure, that's an exact answer. But properties logs, my concern was you look in the back of the book and you're like, what the heck did I do wrong? Where these are just equivalent. It's just by properties of logs and simplified. You can check this with your calculators, but your calculator's not going to write it like this. It's going to put it in decimal form because that's an irrational value.
honestly, that answer might be acceptable.
Absolutely. I know. Hey, I get for years, right? Because it's funny. Students, they're more concerned before the test. They're more concerned about log properties than the actual Calc 2 stuff, right? I get a kick out of that. I'm like, all right, that's the exact answer. It's pretty cool. But you can. Hey, by the way, here we wrote it as natural log. What if this was a plus? What could you write it as? You can do natural log of 3 times 2. It's just, there's only 3 log properties involved in it. If you're curious. Hey, can I raise? All right. This next scenario, everyone, just kind of stands alone. I'll let you look at it. Make sure we got enough board here. This problem one that I made up, this is like number 23 in the textbook. We're going to find the integral of 20 over x minus 1, x squared plus 9. I think I got it from over here. We got to find this one. 20 over x minus 1, x squared plus 9. Most important part's the setup, right? Does everyone see it? The nonlinear factor there? Good eye? So it's just going to make the problem a little bit longer than the last one, right? Who cares? So it'll be a few more extra steps, right? We'll get it. We'll get it. Let me get this started. I just go up to the side. I start thinking, hey, I'll come back to you. I'm going to play with this fraction. This rational expression. We're going to play with it. All right, what's that equal to? A over, and what, just a B? You're good, bx plus c. Over x squared plus 9, there's a nonlinear factor. Let me rewrite this again. That'd be a times a common denominators. These three all the chalk here. X squared plus 9, x squared plus 9, plus bx plus c times common denominators. I have to multiply a x minus 1 and a x minus 1. What's all that equal to? Hey, at least I like the left side. That numerator only has a what? A 20. But there's that right side. It's like, okay. Our goal is just to find letters A and B and C. But look it over, all the denominators are the same. All the denominators are the same. Our focus is now the numerator. Okay. Here's our focus. Just this. I'll write it again. 20 equals A times x squared plus 9 plus bx plus c times the x minus 1. Okay. When in this problem, at some point, we will have to do this process of equating coefficients. But before we do that, can you examine it? You can still get one of the letters, A, B, or C, by doing the if thing. We just go if x equals. You can get one of the letters. You want me to try it over here? Maybe x equals 1. Does it work here? Well, if x equals 1, that becomes 1 minus 1 is 0. 0 times all this becomes 0. We're going to get one of the letters, right? Cool. I do want to point out there's no x value you can let equal here, huh? Not in the real number system. True? So that, but at least, let's get this thing started. I'm going to do it right now. Let's do the if statement right there. If, to be quick, if x equals 1, don't we get one of the letters? Yeah, let's do it, because it's fast. 20 would equal A times up, what's 1 plus 9? 10. plus, my favorite part, 0. What's that? X equals 1, 20 equals A times 10 plus 0. A is just a 2. But I want to get the B and a C. Let's do equating coefficients. So you remember how to do this? That only has a 20 there. I have to distribute all that stuff in the numerator. We'll do it. 20 equals ax squared plus 9a plus, uh-oh, I gotta FOIL that, huh? So when I'm now gonna do the process of equating coefficients, I'm gonna FOIL this all out. What's bx times x? Bx squared minus bx. Almost done FOILing? Here, I'll do this other way. We know a is 2. Minus bx, do the inners, plus cx minus a what? C. Now on the right side, get all your x squareds together. I got ax squared plus bx squared. Get all your things with x's together. Looks like I got a cx minus a bx. And get all your things with constants. There's a plus a 9a and a minus a what? C. And what's this equal to? 20. This is called equating coefficients. Can you get a solo x squared there and a solo x there? That's your goal. Can you get a solo x squared there? What would it be? A plus b times x squared. Plus, parentheses, c minus b times an x. Oh, this is just a constant. Leave it as is, right? And this is all equal to a what? 20? Looking good. Can we do something to the left side if you don't mind? I don't see anything with an x over here, do you? In fact, I don't see anything with an x squared over here. So just I'm going to add this to the left side. Can I just write this? If you all agree. Can I do 0 x squared over here plus 0x plus that 20? Can I think of the left side like that? Everyone see this? Can I think of it like that? Just so I'm ready to equate coefficients. Isn't that what's on the left side? There's an x squared with a coefficient of 0. There's an x with a coefficient of 0, right? So now I can equate coefficients. What's this a plus b going to have to be? 0. What's this c minus b going to have to be? 0. And what's the 9a minus c going to have to be? 20. All right, I'll write that up. A plus b must equal that 0. The c minus b must be equal to the 0. Hey, if you want to put like bars like this to help you see it, feel free to do that for your notes when you go back and look. You know, say 2 years from now, you're tutoring someone. You're like, how did I do this? Maybe just those bars will help you see what we're doing with these coefficients. Those are equal. And what's this 20 equal to? 20 must equal to 9a minus c. Don't forget, we already found one of the letters. Do not forget that. We found a. It's what? So I'm going to start right here. Can we get C? I could. Or can I get B? Yeah, this is going to be easy now. What do you want to start? Because we've got A. We've got A. We can definitely get B and C with all this stuff. Like you could use matrices and stuff to solve this thing. Gaussian elimination. But this is going to be easy. We don't need that. We've got the A value. Want to start here?
You're right.
Start right there.
C minus b equals to 0.
Z minus B equals 0. Thank you. I'll write that. And that C minus B must equal 0. Thank you, Art. You want to start here? If A plus B equals 0 and A equals 2, what's B? B equals negative. If C minus B equals 0, C minus negative 2 equals 0, C plus 2 equals 0, what's C? Do we have all the letters? Let's circle them all. No? And you want to check this, because it should check out. Is it true? Would you check this? We didn't even have to touch this last one, but is it true? We should double check it. Is 9 times that number minus that number equal to 20? We got it. All that work, but we got it. Look at that. I do all the writing, but I know some of you might do like 2 steps at once. So I come back. How do I write this thing? A over x minus 1. What's the A? 2 over x minus 1. Plus.
Negative 2x plus or minus 2.
B was negative 2. And then C was a minus 2. And what's down here?
X squared plus 9.
That's going to be easy. That's going to be a natural log, right? But I'm going to wait till everyone has that written down because everyone, we're going to have to do something about this left one. I mean the left one, the one on the right. Excuse me. This is going to be easy. That's just going to be 2 natural log x minus 1, true? When we perform and find the antiderivative. This, we should split up that fraction. Okay? Now we're going to split up the fraction. It won't be too bad though. And when the hard part's over, we found A, B, and C. We're going to break this thing that was complicated, this rational expression, into partial fractions. And we'll be able to do the integral. All right, but the first thing is, let's write 3 of these separately. What would this be? Negative 2x over x squared plus 9 plus. Now I got to check with everyone in the room. You okay if I erase this? On the right, anybody need to snap themselves on this? Not video.
Any particular reason you factor the negative?
You can. You absolutely can. In fact, I'll do that. I'll put that negative 2 there. I think it's a great idea.
Would you also need minus 2?
Yeah, so you can put a negative 2 here, and then we'll put this over that. Everyone okay if I erase? All right. Can we get some room? I'm going to use your suggestion. You're saying put plus negative 2 integral of x over the x squared plus 9. And then again, what's the last part? Minus a 2 times the integral of a, what would this be? 1 over x squared plus 9. But I want to make sure everyone's okay with how I broke that into 3 fractions. All I did was split that fraction up, right? Well, we have to. We have to do that. We have to split it up so we can integrate. Well, is everyone okay that people are recommending, hey, I like to put constants in front? You surely can. Negative 2x in front, but that x, I mean the negative 2 in front, but the x has to stay. And in this case, you can take the negative 2 in front of the integral symbol, but a constant of 1 would be up there. Now, believe it or not, everyone, I think people in this class have never seen this one before. So I'm going to start this. We'll talk about that. It's actually introduced in this section. Who's ever seen the integral of x squared plus 1? 1 over x squared plus 1. Ah,